All right, so in the last part of this lesson, we're going to go over the second derivative test. So what second derivative test formally says is that if you have a function f such that the first derivative at a point c is equal to 0, and that the second derivative exists on this open interval that contains c, then if the second derivative at c is positive, then it's going to have a relative minimum at c. So at c f of c, there'll be a relative minimum. If the second derivative at c is negative, then it's going to have a relative maximum at c. So at the point c f of c. Now, if the second derivative at c is equal to 0, then the test fails. So it doesn't really tell us anything. It can have a relative minimum or a relative maximum or neither. When this happens, you have to resort to another strategy. So we could probably, use, the first derivative test that we learned earlier. So let me draw a little sketch of like what this means and why this works, because it's actually pretty simple. So I think I have a little sticky note here. Let's say we have point C, f of c, and if we know the second or the first derivative is 0 at c, then that means there's like going to be a horizontal, tangent line there, because that's what it means to have first derivative is 0. Now, if at this point we find that the second derivative is positive, that means that it's going to, be concave up. That's what concave up or second derivative means to be positive. So that, that'll be the bottom of this, parabola looking thing essentially. So that's going to be a minimum. If this, again, if it's a horizontal tangent and we find the second derivative is negative, that means it's concave down there, going through there. And then so that's going to be a relative maximum. So that's all that's saying. So let's go ahead, let's go through practice problem. That's always the best way to really understand these concepts. So we're going to apply this using the second derivative test to find the relative extrema for this function. So the idea is to find the critical points of the function, just like usual. So find where the first derivative is undefined or where it's equal to 0. Then at those critical points, what's going on here? Will blurring up on me. There we go. So we find the critical points. We check the critical points to see what's going on with the second derivative there. And if we find that the second derivative is negative there, that tells us there's the maximum. If we find it's positive there, we're going to find that there's a minimum. Let's first find the derivative. F prime of x. The power rule will be negative 15x to the fourth. That's 15x squared. Find the critical points by setting this equal to 0. So we can solve for the zeros of this equation. We can factor out a negative 15x squared from here. We'll have negative 15x squared times x squared minus 1. That's going to be factored to negative 15x squared times an x minus 1 times an x plus 1. So you can see we're going to have 3 zeros. 0 at 0, 1, and negative 1. We're going to have x1, we'll say 0. X2 is negative 1, and our third possible value, or our third value we want to check, is 1. So we want to see what's up with the graph at these 3 x values. So we're going to find the second derivative equation and evaluate them at 0, negative 1, and 1. So it's second derivative x. Differentiating this again, give you negative 60x to the third plus 30x. And let's evaluate the second derivative at 0. So second derivative, oops. Second derivative at 0. Second derivative at -1. Second derivative at 1. Okay, so we plug 0 into here. We'll get 0, the 0 will get 0 again, so that's pretty straightforward. So we got 0. Plug in -1, we'll get -60, and -1 cubed, so -1 plus 30 times -1. We'll get 60 minus 30, so we'll get 30. And then we'll evaluate at 1. So -60 times 1 plus 30 times 1. So we'll get -30. So let's see what's going on here. So the second derivative at 0 is equal to 0. So here, that means that the second derivative test fails. Second derivative test fails. So that means there could be a minimum or a maximum or neither at this point. We don't know. So we're going to need to resort to the first derivative techniques that we did in the earlier sections. First, let's go to these ones, then I'll go back to that. So at second derivative at -1, we get positive 30. So since that's positive, that means the graph is concave up here. Positive, a smiley face. And so this tells you that there's a relative minimum at -1, f of -1. So that helps us figure that out. And then for the last value for f double prime of 1, we got -30. So then this means it's concave down there. So then we're going to have a relative maximum there. Let me go over here. We're going to have relative max at 1, comma f of 1. So we found two relative extrema with the second derivative test. That was useful. And now let's go and analyze what's going on at 0. So since the second derivative test fails, we're going to do what we did in the previous lesson, where we figure out what's going on with the first derivative before this point and after. So we're going to break the intervals up from negative, or well, not from -infinity, but just from this point to 0, and then from 0 to 1. So you just want to see what's going on there. So let's set up a table. Our intervals. So we're going to go from -1 to 0, and from 0 to 1. Test some value. Test some value in this interval. So let's just do -1/2 and +1/2. Let's see what the derivative, first derivative is, what the sign of that is. Okay, so we want to find f prime of -1/2, f prime of -1/2, and f prime of 1/2. Right, so f prime of -1/2, plug -1/2 into the first derivative equation, up here or up here, doesn't matter, whatever is easiest for you to evaluate. So -15 times -1 to the fourth. -1 to the fourth is just 1. Let's write that as 1. So -15 times 1 plus 15 times 1 because -1. -1 squared is +1. So negative 15 plus positive 15. That's sweet. Negative 15 plus positive 15. Oh, what the? I goofed. Oh my god. I'm supposed to plug in negative 1/2 there. What am I? Ugh. Negative 1/2 to the fourth plus 15 times negative 1/2 squared. Sure. So let me evaluate this. I'm gonna go up. I'm gonna go up here. Take this up here as fast as it stays. So negative 15 times negative 1/2 to the fourth. So it's basically negative 15 times 1/16 plus 15 times 1/4. So you can use your calculator if you need to. But this is going to be a positive number because you'll have negative 15/16 plus 15/4. Negative 15/16 plus 15/4. So again, you just care that's a positive number. So we're going to just put greater than 0. Greater than 0, so that's positive. So I'm going to put positive there. The plus sign. And then let's figure out what's going on at f prime of 1/2. I'm going to plug in 1/2. There's no difficulties today. So I plug in 1/2 into the derivative, so negative 15 times 1/2 to the fourth plus 15 times 1/2 squared. And it ends up being the same thing because, squaring it and raising to the fourth power leaves it all positive. So then this, is going to be, we can just say a positive number, positive. So it's positive here as well. Then what's the graph doing there? That's right. The graph is going to be increasing here, and it's going to be increasing there. It's increasing, the whole, throughout. So there is not going to be a relative minimum or maximum at 0. It's increasing and increasing. So good thing we checked using the first derivative test, because again, the second derivative test doesn't tell you anything. We find that it's 0 there. Now, if you want to take the extra time to find those values, I recommend it, especially when you first start doing this, or reinforce it with a graphing calculator. But let me just draw a sketch of what's going on. So with this function, we know we have an idea of what this stuff is telling us. So we know there's a relative max at 1 f of 1 and a relative min at -1 f of -1. So if I draw, let me draw like a little sketch down here of what this is going to look like. So it's going to go through 0, 0. You can just plug 0 into the graph. Let me put that just like old school plug 0. You get 0, 0. Now, relative minimum of -1 f of -1. F of -1. If you evaluate that, you'll get that f of -1 is -2. So then there's going to be relative minimum at -1, -2. So go into the graph, let's say -1, -2, something like that. So -1, -2. And then there's a relative maximum at 1 f of 1. You plug 1 into the equation here, you'll get that it's -3 plus 5, so you'll get that it's 1, 2. So at 1, 2. So at 1, 2, not drawing a scale, we'll have a relative maximum. And so, let's see if we can figure out what this is doing. If this is concave up all throughout, if it's concave up, to here up until here, and it's increasing there, the graph is going to be doing like this sort of thing. The graph is going to be going like this. Now we don't know about the inflection point because we didn't figure it out yet. It's going to be doing something like that there. And then over here, it's concave down because we have, you know, a relative maximum there. It's going to be doing something like that. And it's going to be like going like this. Don't worry about getting a clear, precise graph at this point, because you know that's actually the goal by the end of this chapter, is to be able to graph a function by hand. But let me take a minute and show the graph, show you what it looks like on the graphing calculator. And so you can see, like, you know, this graph is kind of doing what I have here. See the relative minimum at that point. You can go even further and analyze it if you like. Minimum. The minimum -1, 2. You can see it's like concaving up, then concave down. It's increasing all through, and then your relative maximum. Up there. But you know, this is just something extra, because you know it's always good to reinforce your math work with the graph. It's really going to help you understand it. But there you go.